In this video, we're going to look at the standard form equation for a line. So the standard form equation for a line is ax plus by equals c. A, b, and c can be any numbers except a and b can't both be 0. Otherwise, neither x nor y would appear in the equation. Here's some examples of standard form lines. 4x plus 5y equals 20. So here we've got a is 4, b is 5, c is 20. Negative 2x plus 6y equals negative 4. A and c here are negative, that's fine. 0.4x plus 0.85y equals 10. A and b or c could be fractions or decimals. 4y minus 2x equals 9. It's okay, and it's still called standard form if we write these terms in the reverse order, so the y term comes first and the x term comes second. It's still considered standard form. 2y equals 10 is standard form. Here the a is 0, so that this term is missing. It's 0x, but we don't need to write that. And negative 8x equals 1 is also standard form. In this one, b is 0, and we don't write the missing term. So advantages of standard form lines. One is any line can be written in standard form, including vertical lines. We more typically use slope-intercept or point-slope form for lines, but since vertical lines have no slope, their slope is undefined, we actually can't write vertical lines using slope-intercept or point-slope form. But any line, including a vertical line, can be written in standard form. Another advantage of standard form is that they arise naturally in certain sorts of applied problems where we add two quantities computed using a rate to get a sum. We'll see some of those in the example videos. Disadvantages of standard form. It's not unique. If you multiply both sides of this equation by a non-zero constant, you get another equation of the same line. For example, 3x minus 4y equals 10. If we triple both sides of this equation, we get 9x minus 12y equals 30. So the equations look different, but they represent exactly the same line, which can be confusing. Another disadvantage is a, b, and c, these numbers that you see, like the 3 and the 4 and the minus 10 up here, they don't have any nice geometric interpretation. They don't let us easily picture something about the line graphically. Unlike slope-intercept form, for example, y equals mx plus b, where b is the y-intercept. You can look at that number and know something about immediately what the line looks like. M is the slope. You can look at that number and know something about the line looks like. These numbers here don't have any immediate geometric context. So I want to look at how do we graph standard form lines by doing an example. I'm going to graph the line 4y minus 3x equals 18. Some students always rewrite every line as slope-intercept form, y equals mx plus b, because that's what they're most familiar with. But I strongly advise against doing that. I think it's a bad habit because it makes extra work for you, and also you can make algebra mistakes in the process of rearranging this equation to be in this form. Instead, what I suggest you do is just plot the x and y intercepts and draw the line through them. After all, we only need 2 points to draw a line if we're confident that we have those 2 points plotted correctly. So remember, the x-intercept is on the x-axis. And any point on the x-axis, y is going to be 0. Likewise, the y-intercept is on the y-axis, and for any point on the y-axis, the x-coordinate is 0. So to find the x-intercept, we just need to plug in y equals 0. And to find the y-intercept, we just need to plug in x equals 0. And those lead to very simple equations to solve in this form. If we put in x equals 0, then this 3x becomes 3 times 0. So this term is just 0, and it goes away. We get 4y equals 18. So y is 18 divided by 4, which is 4.5. And if we put in y equals 0, then this term here becomes 0, and we get negative 3x equals 18, so x is negative 6. And I often track all this information with a little t-table. Looks like this. When x is 0, y is 4.5. When y is 0, x is negative 6. And then these 2 points are on the line. And because this algebra here is pretty straightforward. I'm very confident that these are correct. So 0, 4.5 is right there. Negative 6, 0 is right there. And so therefore there's the graph of this line. So every point on this line satisfies this equation. If you plug in the x and the y coordinates, it makes it true. Now there's only one slight catch with this method for graphing. If the constant on the right is 0, then the line will pass through the origin. So the x-intercept and the y-intercept are both right here, so you only get 1 point. Let me show you an example of how I handle this case. Let's plot 2x plus 5y equals 0. If we try the method I showed you, when we put in x equals 0 and solve, we get y equals 0. And likewise, if we put in y equals 0, we get x equals 0. So that just gives us 1 point. So we need another point. A quick trick, it's not critical that you use this trick. You can plug in any other number you want besides 0 to get a second point on this line. But a quick trick is take the smaller coefficient, change its sign, and put it over here. So I'm going to take this 2, put minus 2 here, and you'll see that works out quite nicely. If I let y equals negative 2, this second term becomes negative 10, so I get 2x is 10 or x is 5. So that works out very nicely. So that means here's my t-table 0, 0, which I've already plotted, and then when x is 5, y is negative 2. That's this point here, and so there's the graph of the line 2x plus 5y equals 0.